So in this video, I'm going to be going over some concepts of transformational geometry, and this topic will likely be split over two videos, but most of the theory will be in this one. So to start off with, I'm going to define rigid motion, and so this phrase shows up in a lot of the Regents exam questions, so it's good to know exactly what they mean when they're saying this. So rigid motion is a type of transformation that I'm going to rewrite preserves distance, congruency, angle measure, size, and shape. So even though we're talking about transformational geometry, which is like any transformation, rigid motion is a subset of these transformations. Specifically, it's a type of transformation where one way to think about it is if you cut out the shape and then we're able to manipulate the shape in a way you're able to rotate it, move it, flip it, and then that final image is the new shape. That's a rigid motion transformation because you didn't change the distance, you didn't change the angles, you basically just moved the shape around. So that's a rigid motion. So for example, this B is a rigid motion transformation of this A because I just moved A over. But let's say that I created a shape C, and C is also moved over. It's over here. But actually, I'm going to make C bigger. This is no longer a rigid motion transformation, even though it's still a transformation. This is still some kind of translation. Sorry, it's still a transformation. It's still a translation. B was just a translation of A. It's still a translation, but it's combined with the dilation, which is why it's a different size now. So this is rigid body. This is not, but they're both transformations. So the kind of like the types of transformations that we're going to be going over are reflection, translation, rotation, and dilation. And so dilation is the only one where it may or may not be rigid, but motion likely isn't, but we'll get into that. So the first one we're going to be talking about is reflection. Now reflection is like a flip. So let's say I'm working with this little bean shape and I want to flip it over the y-axis. So if we look at that red point and I want to flip that over the y-axis, what I do is I go to the y-axis a certain distance and then I go the same distance away from it and I draw the point. Now intuitively you might realize that this new point will be at the point 1, 1. So basically if I do that with every point in the little bean shape figure, I'm going to get an image that kind of looks like this. Not perfect because I'm free drawing, but basically it's a mirror image over the y-axis. If I was drawing this on a piece of paper and I folded the paper in half vertically along the y-axis and trace this over to the other side, I would get this. And that's a reflection over the y-axis. Now, what is this? How do I translate from xy, these coordinates, to be the reflection over the y-axis? Well, when I was drawing that little red point over, oh, sorry, I didn't mean it. What I wanted is I wanted the same height, I wanted the same y coordinate, but I wanted the x coordinate to be the negative of the original x coordinate because that's how you get to the other side of the y-axis. So that means that xy goes to negative x, y. Now, reflection over y-axis, a very similar idea, but now instead of wanting the height to be preserved, the same y-coordinate, instead I want the same x-coordinate. So I keep that, and I want the y-coordinate to be the negative. And that's because if I'm going from the top and I want to go to the bottom, I want to negate it. Conversely, if I want to go to the bottom to the top, negate it again. That's another thing I should know. So with this, I have this reflected image. Now, if I do the same reflection back, I'm going to get the original image. If I do, let's say I have this reflected image and I want to do the same reflection over the x-axis. So these coordinates are all negative x, y in reference to the original coordinates. Now to reflect over the x-axis, I do negative x and keep y, which is just x, y, the original coordinates. So one thing to note about reflections is that if you reflect something twice over the same line, you're going to get the original image. So continuing, those are reflections over the x and y axis, pretty standard. But you can reflect over any line. So if I reflect over the line y equals x, now that is not an axis that's automatically drawn on coordinate systems, but I can still represent the axis of rotation. In this image, I drew a little dashed line to represent the line y equals x, and I want to rotate that heart shape. So again, imagining folding the piece of paper in half along the dashed line and tracing the heart over to the other side, it's gonna look something. Again, I apologize, this is not perfect, but the reflected image will look something like that, um, with the blue point being around there. So that was just me eyeballing it intuitively what it would look like. But if I'm trying to be rigorous, kind of more arithmet arithmet arithmetically, if I want to translate from x y, well, I just told you y equals x, so y becomes x, and x equals y, so x becomes y, and that's how you flip over the line y equals x. Now, if I want to flip reflect, I'm using them interchangeably. Now, if I want to reflect over the line y equals negative x, again, I'm telling you y equals negative x. Now, what about x? Well, y equals negative x, negative y equals negative x equals x. So x equals negative y. So that's reflecting over the line y equals negative x. Now, one last reflection I want to go over is reflecting across the origin 0, 0. So I have the origin 0, 0. And I think it's important when thinking of this reflection to actually consider. Well, I'm going to be doing points. Could be figures, but considering things to be reflected in different quadrants, I'm going to be thinking of reflecting things in quadrant one and quadrant two. And the reason why I say that is because let's start with the red point for now. When I'm reflecting the red point across the origin, I'm coming in from this angle to the origin, and I want to reflect across it. So I'm going to reflect across this line. That actually, the line is y equals negative x. Because I'm going into the origin in like I guess it would be the shortest the shortest distance to the origin, and then I'm going that same distance out in the opposite direction. And the reflected point would be in quadrant 3. It would actually be negative 1, negative 1. But if I'm trying to reflect from quadrant 2, the point negative 1, 1, that blue point, I'm going into the origin. I'm actually going to be reflecting across this line y equals x. And I'm going to get to the point here. It'll be 1, negative 1. I actually think a more intuitive way of thinking about reflecting across the origin is to think of it as a rotation of 180 degrees. If I'm reflecting across the origin, that's the same idea as folding the paper in half. Whichever way the point or figure that you're reflecting is not on the axis of rotation, but like that axis still goes directly through the origin, and tracing it to the other side. Um, but so quadrant 1 will map to quadrant 3, quadrant 2 to quadrant 4, and the reverse as well, because as I said, reflecting twice is the same as the original. So think of this as like in terms of xy becomes negative x, negative y. And that's just how you get to that opposite quadrant. And again, this is the same as as rotating by 180 degrees. I'm going to get into rotations later. That will come up again. Now, the second transformation I want to go over is translation, and that's a shift or move. So let's say I have this trapezoid. Oh, sorry, this coordinate was written in. I have this trapezoid, and we have the coordinates of the corners of the trapezoid, and also the midpoint of the base of the trapezoid is at 0, 0. It's at the origin. But let's say I don't want the trapezoid to be at the origin. I actually want I want that midpoint in the base to be at the point 3, 3. Who knows why? I just do. Well, then I'm just going to move the trapezoid over. So I can do this. Well, I could just manually, individually move the um, move the corners over and then draw in the lines. So starting with this corner is 2 units to the right of that midpoint, and it has the same same y coordinate. So if I repeat that to the corresponding coordinate here, 2 units over, 3 plus 2 is 5, and the same y coordinate, 5, 3. Now if I go to this corner, that's 2 units to the left of that midpoint with the same y coordinate. So repeating at the corresponding coordinate, 2 units to the left, 3 minus 2 is 1, and the same y coordinate is 3. Now just to wrap up, this other corner is 1 unit to the right of that bottom one, this bottom one, and 1 unit up. So if I'm going to this, if I'm going to this corresponding corner, and I'm looking at it in terms of this one, 1 unit to the right, 1 plus 1 is 2, and 1 unit up, 3 plus 1 is 4. And then finally, this is 1 unit to the left of that one, and 1 unit up. So 1 unit to the left, 5 minus 1 is 4, and 1 unit up, 3 plus 1 is 4. So that was just me moving the corners, and then I just drew in because that preserves distance and angles. If I have like the same coordinates, I just translated them all. Now, what this is, even though I only showed it for the corners, is what I actually did is for each coordinate, I translated 3 units to the right and 3 units up. So that's a translation of x plus 3, xy goes to x plus 3, y plus 3. Now, this is a specific example, but in general, a translation can be represented as xy goes to x plus a, comma, y plus b, where a and b are numbers. Now, they could be whole numbers, like 1, 2, 3. They could be fractions as well, or they could be negative numbers as well. Now, what does the positive versus negative mean? Well, when we're thinking about that x coordinate, a positive a means we're translating to the right. And that's because when you increase the x coordinate, the point moves to the right. Now, a negative a means translation to the left, and that's because when you decrease the x coordinate, that's a translation to the left. Now, if we think of y, a positive b is a translation up, because when you increase the y coordinate, that's translating up. And a negative b is translating down, because when you decrease the y coordinate, that's going down. So now rotation, the next transformation, which is also we're still in rigid motion, that's a turn. So I have this little rectangle in quadrant 1, and I want to rotate it by 90 degrees. Well, when we think about it, that's going to end up in quadrant 2. Now, that's very intuitive because each quadrant encompasses 90 degrees. So if we're in quadrant 1, to rotate 90 degrees, also, I'm implying rotating counterclockwise in this specific case. The standard is that rotation, just in general, is automatically counterclockwise. It's great to specify counterclockwise versus clockwise. You should in your answers. I'm just warning you, if a question does not specify the direction, it's most likely counterclockwise. So rotating 90 degrees, we know it can no longer be in quadrant 1 because the entire quadrant is 90 degrees. So it has to be in the next quadrant over. So that's going to be quadrant 2. And if I just eyeball it, it's going to look something like this. Pretend that that's the same height as the other one, with that red point ending up there. So when I rotate by 90 degrees, what happens is that the horizontal becomes vertical and the vertical becomes horizontal. If you take your pencil and you rotate it 90 degrees, then what happens is I'm thinking you're holding the pencil vertically, the short end goes down, the short end, which is on the bottom, it now goes to the side. So that means that what was originally horizontal became vertical. And then the long end, which was what was up first, is now flat. So the vertical became the horizontal. So that means that, because of this, the x and y are somehow going to have to flip. But if I just do xy goes to yx, that's actually, as we recall, that's reflecting across the line y equals x, which is not 90 degrees. Like I said before, it just goes over to the next quadrant. So how do you get it to just go over to the next quadrant? Well, you want the x coordinate to be negative if it was once positive. So you want that. You want it to be negative y now. And you may be wondering, but hey, hang on a minute. Now that I'm in quadrant 2, if I want to rotate 90 degrees, but I don't want, that doesn't mean that the x coordinate is going to become negative. Well, because you're flipping again when you rotate 90 degrees again, um, that won't be a problem. It's going to be negative x, negative y, which is exactly what we wanted. So this was quadrant 1, 90 degrees, quadrant 2, 90 degrees, quadrant 3, and then another 90 degrees. Again, that negative y x, negative negative y, comma, negative x. That's y. Oh, uh, hold on. Hold on. XY. Oh, wait, I'm sorry. It should be negative xy. Wait, xy goes to negative y. Oh, no, I'm sorry. Sorry. I lost my train of thought. So xy goes to negative yx, so that's clearly in quadrant 2 because we have a negative x coordinate, positive y coordinate. Then 90 degrees again goes to negative x, negative y. That's clearly in quadrant 3 because both coordinates are negative. And then 90 degrees again, that goes to negative negative y, which is y, negative x, and that's clearly quadrant 4 because the x coordinate is positive and the y coordinate is negative. Now I kind of just spoiled it. Also, we looked at it before, but rotating by 180 degrees is just negative x, comma, negative y. Again, that was before I talked about rotating about the origin. Reflecting across the origin was the same as rotating by 180 degrees, and it was this. But also, uh, a rotation 180 degrees is just 2 rotations of 90 degrees. And then finally, a rotation by 270 degrees. Well, again, I kind of spoiled it. If I do 3 rotations of 90 degrees, I get that it's negative x, negative y. Sorry, negative 1, 2, 3. Sorry, y negative x. But another way to think about it, as opposed to a composition of 3 rotations, we can think of a composition of 180 degrees and 90 degrees. So rotating xy by 90 degrees and then by 180 degrees. Well, rotating xy by 90 degrees, again, that's going to produce negative yx. And then rotating that by 180 degrees, that's going to be negative x, comma, negative negative y equals negative x, y. Just, wait. Oh, sorry. I flipped when I did not need to, sorry. Negative of negative y, comma, negative x, which is y, negative x. Just to think of trying to incorporate compositions of transformations as well, which I'll talk about a little bit more later. And then the last transformation I'm going to go over in this video is dilation. So this one we have to be careful with because dilation is not necessarily a rigid motion, because what dilation is that it's an enlargement or a reduction. And again, rigid motion, we want it to preserve distances. So what I was saying before, like you should be able to cut out the image and just scooch it over a little and get the new image, and that's rigid motion. Well, dilation, not necessarily. So I have this triangle, I can enlarge it. So keeping it just on top, enlarge it, or I could make it smaller. Oh. So what this is represented as xy goes to kx comma ky, where k is some number. If k is greater than 1, it's an enlargement. So like here, k was probably around 2 because it's about this side is about twice as long as the original. Or if k is less than 1, it's a reduction. And here, k was probably around 1/2 because it's about 1/2 the original. And so that's it for this video. The next video, I'm going to cover a couple more concepts and do some examples.